Now that the guest of honor is here, I'll re-announce the talk.
I try to skip.
Our concluding talk of the afternoon is by Tian from Princeton, and he'll be talking about conic Kähler-Einstein metrics.
Thank you. So anyways, it's a great pleasure to come here to give this talk. And so certainly I'm grateful to Blaine for many things. And one of the things I should be grateful is I guess Stony Brook made me a first tenured offer. I'm sure Blaine played a big role in that, in making that offer. And in that time, I feel very much appreciated. And so I certainly like to come to speak in his honor. So. And also it's I guess 10 years ago I came for his 60th birthday conference. So after 10 years, came for 70th birthday, and the same thing happened. And last time I flew back from China, and this time I thought I could have come from Princeton, but something happened. I had to be in China last week and this week. So actually I flew back from China again. So and I will fly back. So anyway, it's just I feel it's and I got this help from Blaine many years ago, and I certainly hope to make a return. This is a really small return, and hopefully I can do it and in 10 years again. So and also it's and I was wondering what I'm going to talk about today. So certainly, naturally, I could talk about the calibration, and there were a lot of talks today, G2 and Spin 7 and so on and so on. And there are a lot of, there is a key problem in all these approaches, and in order to make it geometrically useful eventually, is this compactness theorem. You need to do some analysis. So to make things work, actually not only compactness, it's also some transversality, because if you assume everything nice, you can do implicit function theory. But when you try to construct the invariants out of that, it's not that nice, and it's not nice at all. Even transversality theory is not clear, and when you especially have a calibrated variety, which might have singularities, and how do you say you can make it nicer enough to construct invariants? But anyways, unfortunately, I haven't made substantial progress on this problem in the recent years. So I thought maybe I'd do something else. And today I will show you something I did recently. And I want to claim a theorem here, which I have been working on for many years. And at least 20 years when I was here. So in this sense, it's okay. It's a cycle. So I finish this, and then I move on. Maybe I can have more time to do a calibrated geometry. So this talk will be maybe compared to some other talk, maybe a little bit detailed and technical, and I apologize for that, since this is the last talk, and a special to such a distinguished audience. So, okay. So first, let me say what is a Keller, Cortical Kähler-Einstein manifold. So call it a Keller metric on M. So in this talk, I assume M is a Keller manifold, and D is a divisor. So a smooth divisor, this is a complex hypersurface, holomorphic submanifold, and the complex codimension 1. So a conic Kähler metric on M with angle 2 pi beta along the D is a Keller metric on M minus D, which asymptotically equivalent to a modal metric. Okay, so of course this modal metric is also a Kähler metric, and so this we call the cortical angle because if you just look at this piece, which is transversal to this divisor, is singular at z1 equal to 0 and has a cortical angle of 2 pi beta. Okay. So this is a natural class of metrics, and even though they are not smooth, but they are quite natural to study. Okay.
Why do you assume beta is less than or equal to 1?
Okay, where is that? This is the beta. Let's make in general. You don't need to assume. You don't need to assume anything on beta. But when the beta falls into this range, in some sense, this conic is positive curved. If you go beyond that, the analysis is very different, and even the S2 case, even on a Riemann surface, it's not completely clear how to do it. So let's stay in the case we can do better. Okay. So.
These talks, there's a lot of positive curvature in the singularities.
Yeah, it's that's because that's a remaining case to be studied. Other cases are you will see that, so it's easier. So this is like along this D, so you have a cone angle of 2 pi beta. Okay, so you have a family of 2 angles. So a cortical Kähler metric can be given by its Kähler form. So namely, it's given by some this special. So giving a Kähler metric locally is given by Hermitian positive definite matrices. So you can still define by this. Okay, and Kähler means this is closed form. Of course, this may have a singularity, so it has to be understood in the sense of currents and so on. Okay, so it is it is sorry. So so it has a Kähler class. It has a class as before. So just pretend that's a smooth case. So even though we have this singularity, the singularity, as I said in the model case, is not that bad. It's not bad. First is integrable, for example. So you can still make sense of a lot of things. Okay. So you still have a cohomological class, and we call it a Kähler class. Okay. So it's X is very similar to a smooth case. So a cortical Kähler-Einstein metric is a Conic Kähler metric, which are also Einstein outside cortical points. So it satisfies this equation as currents. So it's a Ricci curvature equal to some constant multiple of omega, and this is understood as a delta function along the D. Okay. So outside D, this one has no support. So this is actually just Einstein equation. So this whole thing is understood as globally as a current. So as integration along the things. Okay. So you take some test function, you wedge with this, a test form, wedge this, and integrate against the manifold.
So what's the definition of the left-hand side?
Okay.
We worry about nonlinear operations applied to currents.
Yeah, it's I guess did you go to Reese Harvey's talk in the morning? That's they did much more than this. So this is I was just joking. Okay. Oh, so you start with any smooth form with compact support. This is understood in the sense mu omega. D. Okay. For any smooth form of 2n minus 2 degree, which complex.
Confusing, Dennis, is that in the Kähler context, you could think of the Ricci form rather than the Ricci tensor as the curvature of the canonical line bundle. And that's easier to make sense out of than the Ricci tensor in a kind of naked way on the level of Riemannian metrics.
So, okay.
I mean, it's not the. No,
Okay, that's
Just, no, but wait, my question is this really the trace of the generalized nonlinear curvature?
it is a trace, but so this term here. So you understood. Suppose it's let's make it locally. So this is dd bar of a log of volume form. But since this one has a singularity here, so this one has a pole along the, not quite the pole, but it has a singularity along the d. So when you take a log of dd bar of log things, it has a singularity. So locally you understood this is this integral means this. Sorry, this integral means that. Sorry, is that clear?
There's a log. Have you written a log there?
Yeah, it's a log of determinant of a volume form, because dd bar of this is a Ricci curvature. So locally, Ricci curvature is given by this. And this is smooth form. So this is smooth. dd bar of that is smooth. So this singularity is not that bad. It's not logarithmic singularity. So this is integrable. So this makes sense. And you understand the integral as that. So then this formula simply means this equal to that.
The volume form is a current which has a singularity, right?
Yes.
You can't take logarithm of a measure.
No, it's the logarithm. The determinant of the metric is the volume.
I said locally. Globally, you let's do it first locally. Okay, locally you can write this. So the volume form is a function. You think that. So let's just make this support to be very small. Then this is you can just work in a one coordinate chart. Okay.
Yeah. The volume doesn't have any
That's right.
as a density function.
Mm-hmm. Okay, thanks. Okay, so let's at least clarify this. I try to hide of some of things. So anyway, in case n equal to 1, this is where studied problem. So say omega, this homology class is a positive generator of this, namely Keller class is a positive generator of this. So then you can compute mu in terms of genus and the degree of divisor and the degree of divisor. And the divisor now is just a bunch of points. So if a mu less equal to 0, there's a unique conic metric of a constant curvature, mu in the given class, okay, giving Keller class, or in this case, just giving volume form. So if a mu is positive, there is a unique spherical conic metric if and only if for each I, this actual condition satisfied. Okay, so when the mu is negative, that's like a flat case or elliptical hyperbolic case, and there's no actual condition, So you can always find a metric with a cortical angle at this giving point, Okay, and in a positive case, it's not always true. It's so you need this actual condition. Those are classical results. So what I'm talking about here is, for example, in a positive case, you have a sphere, okay, S2, and you look at you have these points where you at those points, instead of being smooth, the metric look like cone angle with giving cone at pi. So then you ask whether there's a spherical metric outside this point with prescribed cone angle 2 pi beta I at those points. And this, even in the one dimension, it becomes much less trivial. So you have this actual condition. So actually, for many years, even when I was here, it's a long time ago, and this is like always example which motivates me, and try to interpret this in the proper way and extend to high dimensions. Okay. So in the modern language, this condition simply means this is K-stable. Okay. Or more precise should be say log K-stable, because it's not a smooth case. Okay. So in the high dimensions, there are some recent, in the last 2 years, there are some recent progress. And this, the first, like Simon Brando proved for rich flat conic Kähler-Einstein metric with cone angle less equal to pi along the D, and with some restrictions. So he only considered there are some actual conditions. And around the same time, Jeffrey Mazel and Rubinstein proved the general case, proved general case. And they also have a result in the case of, for general case for non-positive scalar curvature. And in their proof for general case, there's also contribution from Chernyi, because you need to construct some approximate metric. Okay. And there are also related work by those people, but they didn't quite give a precise description of this structure along the D. So what's important here is we would like to have a metric which has a precise conic behavior along the device, because if you don't require that, indeed there were a lot of previous work on the for Kähler-Einstein metrics on the non-compact manifolds. Okay, So there are at least 2 motivations to study conic Kähler-Einstein metrics in high dimensions. One thing is I mentioned because it's related to my previous job here. So there is a famous conjecture. I think it's called Green-Griffiths conjecture, which says there are only finite many rational curves. Rational curves means holomorphic S2 in a complex surface of general type. Okay, and Bogomolov proved in the 80s, or maybe even earlier, that it's true if a C1M square, M is this complex surface, is bigger than a C2. Okay, so this is topologically means the index is positive. Okay, it's positive. So in 1994, I observed if I have a conic version of Miyoka-Yau inequality, so I don't want to write out. Okay, and anyway, and I'm sure many people in the audience can write out the so anyway, I wrote in some exploratory papers. So then Bogomolov's theorem still holds, even if this equality holds. And moreover, one actually has an effective bound on the number of rational curves if this Bogomolov condition holds. Because then I thought one should construct a Kähler-Einstein metric with conic angles. Then, as a standard practice, you can derive this inequality. So then I give this problem to one of the students here. I shared with Blaine and Tian Jeffrey. I thought that was easy problem. I shouldn't say easy, even for thesis it's not easy, but I thought it's a doable problem. And it turned out it was not quite doable. So she made some progress and established some tools, but the problem was not solved until until last year, even for smooth case. Okay, so in general case, you not only need a smooth divisor, you also need actually divisor with normal crossings. Okay, so anyway, but in order to give this application, actually shortly after that, actually, I realized, when talking to Stephen Liu, actually, you don't really need to use a Kähler-Einstein metric to prove this inequality here. You can use some algebraic geometric method, which is more flexible. So this inequality is true, even without proving existence of Kähler-Einstein matrix. Okay?
Always for surfaces.
It's always for surface. You can also have a version of that for high dimensions, except you have more terms. So it's not more terms. It's still 2 terms, but this should be C1 to n, and here is C2 dot Cn to n minus 2. Okay? And the constant depends on n. So anyway, so this is one motivation, and I guess I made a mistake. I thought it was doable, and it was not so trivial in the end. I guess time is quickly. So anyway, more recently, Lawson proposed a new continuity method, which is by using a Kähler-Einstein matrix for solving a following conjecture. It's also a four-cloud conjecture, and I guess it's much younger than a previous conjecture, which says if M is a fellow manifold without holomorphic vector fields, then M admits a Kähler-Einstein matrix if and only if M is k-stable. So this is generalization of this theorem for one-dimensional case. Okay, so that one-dimensional case tells you if there's a spherical metric with a prescribed cone angles, and if and only if it's k-stable. Okay, it's k-stable.
The first place where Donaldson discusses this is actually before the papers of Brendel and Jeffrey.
Yeah. Anyway, here
They actually use some of his ideas in those papers.
I didn't say it's after, so
More recently.
more recent compared to previous slides.
That's what I was arguing with. It's not more recent than the things you were discussing on the previous.
Yeah, I just compared to previous slides. It's for motivation, so it's not for existence. So, okay. even this anyway. So let's go on. My short of time now. So one approach to proving sufficient. So let me go a little bit things about this approach. And before this, let's try to recall a little bit the old approach, which in comparison to Lawson approach. So we consider this so-called O-bounds continuous method. That was first used by O-bound in 1983. So basically, we want to solve these equations, and with T as a parameter, and it's known the set of T which is solvable is non-empty and is open. Non-empty is due to a Calabi-Yau theorem, and the open was proved by O-bound in 1983. So if it is closed, if a K-energy or its Lagrangian is proper, so K-energy is functional such that whose critical point are Kähler-Einstein matrix. Okay, so here I have to hide something. So it's just consider. So it's not uncommon in this conference now. So anyway, if you want to make everything clear, it's impossible. Okay, so K-energy is just some functional which is well defined, and whose critical points are Kähler-Einstein matrix. So in general, K-energy is not proper due to holomorphic abstractions, such as k-stability. That's what basically these kind of abstractions we studied a long time ago when I was here. So I guess I introduced k-stability in 1996, but actually before that I already studied these things in the 90s. Okay. Now formulated algebraically by Simon Lawson in the early 2000s. So actually, my definition is more analytic in the sense it's directly related to properties of K-energy to a K-stability. Okay. So it's basically just the K-stability in finite dimensional case. Okay. So you will see why I came to this K-stability. So assume M is a fellow. So that's like fellow means the first Chern class is positive. So it's like analogy of this field in high dimensions. Okay. So that means this is just a wedge product determinant of a tangent bundle, holomorphic tangent bundle. So this Km inverse is just the following algebraic notation is the tangent holomorphic determine the holomorphic tangent bundle. Tangent bundle. Okay. So in a so this means this is ample. So in my thesis, so I refined the Kodaira embedding theorem. So Kodaira embedding theorem says since this is positive for L sufficiently big, any basis of this will give an embedding of this manifold into CPN. So, but this embedding is not unique because you can choose a different basis. So different basis will give you a different embedding. But then you have if you have two different embedding, they different by automorphism group of CPN. Okay. So because of this, you can get a natural family of matrix. We sometimes called Bergman type matrix. Namely, you take this standard metric, homogeneous metric on the CPN, and this is automorphism of CPN, and then pull back by phi. So to M, you get a Keller metric on M, and then you normalize that. You want the Keller class to be fixed, to be in the first Chern class. So in my thesis, I proved this is actually dense in a space of Keller metrics on M with a Keller class this C1M. So this rho of this 1 over L plus this normalization here. So the K stability is equivalent to a properties of this K energy restrict to this 5-dimensional space for sufficient large L. Okay. So this is the shortest way to define the K stability, which I will not go further to define it. Okay. So then what you do to make it more algebraic, you try to abstract the algebraic information from this. Okay. But analytically, this is exactly equivalent things. Okay. So this implies, since I said the conjecture follows if you follow O-bounds approach, the conjecture follows if you know the K energy is proper, but K energy is in general is not proper. But if you say if you can establish the following conjecture, then you can reduce the properties of K energy to a properties of K energy restrict to this 5-dimensional space for a sufficiently large L. So then you solve the problem. Okay. So that's why I came to this partial C0 as a conjecture. So this is a conjecture which says any omega with a Keller class C1M induce. I define first try to phrase the sentence. So induce the inner product on this space for each L. Let this to be orthonormal basis. So with a metric, you can have an orthonormal basis. So before, in the Kodaira embedding theorem, you take any basis. Now, I want to normalize it. So you make an orthonormal basis. Then you define this function. This function is well defined. It only depends on this metric here. So this function actually, in some sense, can be thought as a pointwise version of Riemann-Roch theorem. Because if you integrate this on both sides along the manifold, this exactly gives you a dimension of this, which you can compute in terms of Riemann-Roch theorem. Okay? Because this ampleness tells you, this positivity tells you this high cohomology group with coefficients in this line bundle vanishes. Okay? So also when I came to this, actually, I also thought this is really like a complex version of hit kernel things. So you actually can have an expansion of this in terms of air. So you can expand this function in terms of air and compute the coefficients. All the coefficients can be, that was proved later, so it's not the canonical order here, okay? So you can compute the coefficient in terms of curvature and derivative of curvature and so on. So then the conjecture says the following. So there are some universal constant such that for any omega with a Keller class, and the Ricci curvature bounded from below by some positive constant, and this is uniform bounded from below. So this conjecture, actually I knew this conjecture even before my thesis. And again, it's not canonical because when I tried to solve this Calabi problem for complex surfaces, I already had these things. Okay, so later I stated this for general case in the 90s. Okay, so this is still open except for Kähler-Einstein matrix, which is very recent. Okay, and for Kähler-Einstein case. So, but Kähler-Einstein case does not guarantee the solution. I mean, you don't give up enough things for using all-bounds continuity method, because in all-bounds method you do get the matrix with Ricci curvature bounded from below, but you don't have upper bound. Don't have upper bound. Okay. If you have upper bound, then everything is okay. Okay. So then. So we see this Donaldson's continuity method. So Donaldson suggests a couple of years ago, if D is a smooth anti-canonical divisor, then there is a complete Calabi-Yau metric, and you already heard about that in some talks. So then it was expected that this complete metric is the limit of Kähler-Einstein metric with conical angle 2 pi beta goes to 0. So you can namely perturb this Ricci flat metric so that the cone angle at infinity along D is small. Okay. So if so, then the set of beta such that there is a conical Kähler-Einstein metric. Sorry, there should be a conical Kähler-Einstein metric with angle 2 pi beta is non-empty. It's non-empty. So, but there is some problem with this approach. Namely, it's not known if every fellow manifold admits a smooth anti-canonical divisor. I guess it will be extremely interesting problem in algebraic geometry. Okay, so I guess in the lower dimensions you can check that, because you can go through examples, go through go through a list of classifications of a fellow manifold, and then you check this indeed is true. So there is a modified version of this Donaldson's approach by Chi Li and Sun Song. They said that if instead of start with a divisor which is anti-canonical, you can allow this device to be multi-anti-canonical. Okay? So in this case, D is a smooth divisor whose Poincare dual is a multiple of a first Chern class instead of Chern class. So then let E to be a set of this beta in this range. So why I want to restrict this? Because I want to stay in the positive category. Namely, scalar curvature is positive or mu is positive. So that's a low bound for that. If this beta is equal to 1 minus lambda inverse, that's just correspond to Ricci flat case, conical case with conical angle. Okay. So E again is such that there's a conical Kähler-Einstein metric. I'm sorry about this. I missed the Einstein here because from now on it's basically always assume a Kähler-Einstein, and with angle 2 pi beta along the D. So then this modified version has an advantage. It's easy to have an initial one. So if a beta sufficiently close to this value, of course on the right hand side, and then E is non-empty. So this is due to a work of Jeffrey, Mazel, and Rubinstein, and also with actual observation by Li and Song. So and E is open. That's proved by Donaldson a couple of years ago. And the beta in the E, if the K energy, so K energy in this conical case, so sometimes called twisted, but it's just K energy in this for conical metrics is proper. So this was proved by Jeffrey, Mazel, and Rubinstein. So I guess even though at that time was a hard problem, in the end was pretty good. Okay. So we have these nice theorems and continuation. So there is also a conical version of this partial C0 estimate, because on the so the definition is exactly is the same. It's the same. In fact, this conical metric is not that bad. It only has a singularity, which is still integrable, because this conical angle is less than is strictly positive. Okay. So in fact, in this approach by this Lawson's approach, you can assume a cortical angle sufficiently close to pi by increase the lambda. Okay. So anyway, so I state this only for Kähler-Einstein matrix. Of course, you can also do the case when the Ricci curve is bounded from below. So this is the same thing. Then this is defined exactly in the same way. Okay. So if this partial serial estimate is true, and if this partial serial estimate is true, so then one can prove that the twistor K energy is proper along the E whenever M is K-stable. Okay, so this is, I don't say it's a proper only along this set for continuity method. And this follows from a result of Lawson and probably some other people. So this result says if M is K-stable, then this is not K-stable for any beta positive. So then the K-stable, original K-stable condition will tell you all the twisted cases are also K-stable. So then you can check this corresponding K energy is proper on the finite dimensional case. So again, the crucial step now is to establish a cortical version of partial C0 estimate. Okay. So as for smooth Kähler-Einstein matrix, we need a compactness theorem of Kähler coding Tian type for conical matrix. Okay. So once you have this compactness, and then by modifying this recent proof of this for Kähler-Einstein matrix, and then can I mean you need to do some modification, but that modification is not completely trivial. Okay, so anyway, so key step is to establish a compactness theorem for Kähler coding Tian type. So what is a Kähler coding Tian type theorem here? So I guess it's Jeff left. He probably sorry for missing the talk here. So so I do a little bit faster now. So since he knows better, well, a couple of people here knows better, but not most people know some technical point here. So let the omega I be a sequence of a conical Kähler-Einstein matrix with a cone angle 2 pi beta along D. We are suppose this converging in this in a Gromov-Hausdorff topology. That's not the assumption. So it's basically you can have that. Okay. So then so this I state this theorem. So this is theorem I try to prove. Okay, and then I tell you what's the difference. Okay. So I say there is a subset, closed subset, and of codimension 2, such that M infinity minus S is smooth. So originally in a Gromov-Hausdorff limit, this space is just some metric space, and this is just a metric function. It's not the Riemannian metric here. So, and the second point, D infinity is induced by Kähler-Einstein metric outside S. And the last one, I say it's a convergence outside this S is smooth. And all these things are proved for Kähler-Einstein metrics by Kähler coding and myself. And I want to extend this theorem to this. And then plus L2 estimate, and which I don't know if I have time to cover that now. So we can prove a partial C0 estimate. So by extension, it's not. So actually, moreover, we can prove if a beta infinity is 1, M infinity is smooth outside the subset, we offer codimension at least 4. Okay, but convergence is still codimension 2. Outside codimension 2 set. Okay, so to prove the above, we need some arguments in the proof of this, but also some new inputs, especially in establishing a smooth convergence outside S. So maybe I say a few words here, just in case some people know the difference. So in one of these, in one aspect, in order to prove this conical version of this compactness theorem, you just try to extend the arguments of Kähler coding and myself and some arguments of Kähler coding to this conical case. And some of these extensions possible. Okay, you just like you want to do a little bit tedious work and try to go through it. So, but there are some points you cannot do trivially, extend trivially. For example, there's one point. There's a 1 point. The 1 point argument is as follows: if the limit has a tangent cone at every point, and if a tangent cone is trivial, then you expect that point a smooth point. And the proof goes as follows in the smooth case, because the volume is preserved by Coding's theorem. So if a volume is if a tangent cone is Euclidean, then the volume of a ball nearby that point is also close to Euclidean ball. So then there is a result of Michael Anderson says then curvature is uniform bounded. Then you can do it. Okay. So then you can say convergence, everything is nice. But if you know, if your space are probably is singular, and you don't have that things. You don't have that thing. So of course in general this is not possible. For example, and so you have certainly you can, for example, you can look at like a sequence of metrics such a cone angle opens up to 2 pi. So in the limit, the tangent plane is trivial, but certainly you cannot bound the curvature here. Even in one-dimensional case. Okay. And in a high-dimensional, it's even more complicated because your divisor is not isolated. It's not 1 point. So this is complex as a hypersurface. But how do you know in the metric limit, this complex hypersurface is dense? It becomes more dense and dense because these are 2 different topologies. One is the Gromov-Hausdorff topology, which is weak topology, and this is complex limit. So indeed, in general, if you don't make any assumption on the D, it's possible, just like this case, it's possible to construct an example, even if a limit is smooth, but none of these things, but the cone angle points become dense and dense, okay, in the metric sense. So one needs to have a new argument. So in order to do that, I want to just tell you 2 ingredients. And the first ingredient is not absolutely necessary, but it's at least for the current argument now, I will tell you when it's necessary, but at least not necessary for all the things I stated later. Okay, my time. So the first thing I want to answer is the following thing. So can one approximate the Cortical Kähler-Einstein metric by some smooth Kähler metric with rich curvature bounded from below? So this is a natural question, right? So of course, in a one-dimensional case, you can always do that. It's trivial because what you do, you have a conical angle here, and you can even make it standard asymptotically. What you do is just round it out, and the curvature will be still positive. Okay. So and you keep this round out smaller and smaller. Eventually goes to a cone. Okay, so in one-dimensional case, it's possible. But in high dimension, because you do it on a divisor, the first things you try, that's what I just thought at the beginning. I gave, again, to one of this my postdoc, one of my collaborators, I said, this must be possible, just do by hands. And locally write into coordinates and try to do it. And after a few weeks, it says it seems to be hard to do it, okay, because you have a contribution of curvature in the divisor directions. Actually, there are also some examples constructed by Simon, which probably make it even harder to do by hands. Okay, but on the other hand, it is possible. It is possible, and it's done by solving a complex Monod-Trumpy equations. So maybe I skip this part because my time is up. So anyway, the answer is yes. Okay, so this in next couple of transparencies, I just try to tell you how to do it. So basically, we can set up an equation. We can set up this equation. So set up this equation, and this equation is an equation for Conic Kähler-Einstein matrix. Conic Kähler-Einstein matrix, And this is nothing, what I did here is nothing really difficulty, because basically just like in a smooth case, you can reduce the existing problem of Kähler-Einstein metrics to a Monchampy type equations. And here you can do that too, here that, except you might have some singularities. Okay? So then to find the smooth metric, what you do is you just smooth out that singularity. So very simple idea. You look at the delta, you put delta in front of that. So you see the difference of this equation from this old one is just make it non-singular. Make it non-singular. I smooth out this function here. Okay, smooth out this function here. That's what I did for H. Okay, and this is some normalization things, and the good things is you can compute if phi delta is a smooth solution of a previous equation, then the corresponding metric has its Ricci curvature greater than mu whenever beta less equal to 1. So not only you can approximate the conical Kähler-Einstein metrics by metrics with Ricci curvature bounded from below, and you can actually approximate it by Ricci curvature with the same low bound. Okay, so I guess that's true in one-dimensional case. Okay, this is also true in high dimension, but you need to solve equations. So again, so this is a theorem. So there is a smooth solution for above equation for any delta less equal to 0. Okay, delta bigger equal to 0. And actually, and this theorem does not depend on sign for mu. Actually, for when the mu is not positive, this theorem is easier to prove, because as we know, to solving a Monchampy equation in the non-positive case, you don't have really much in sometimes much difficult. You have all the estimate available. Just try to repeat what was done in the literature. Okay, but for positive case, you need to do something extra. Okay, because in the positive way there is always a condition. So you want to make sure this K stability condition still works here. So to solve the equations, and indeed it can. Okay, so this part has been written up, so it's okay. And moreover, one can do two things. One can prove actual things, namely you can prove. First, omega delta converges to omega in a smooth topology outside D. This is not difficulty because you just develop some estimate. All estimate developed is outside D. But then you want to do the metric convergence, which is different because this is more like complex limit. You fix the complex structure, you talk about the limit. So this is proved by some sharper C2 estimate. Okay. So anyway, what I try to say is not only you have approximation, and this approximation indeed in the metric sense. Indeed in the metric sense. Okay. So then moreover, we have following things. Not only we have this in the metric sense, also we have this corresponding convergence on the cohomology. So this can be regarded as I said many times before, in 20 years ago when I was here, this is thought as a metric version of flatness for family of algebraic manifolds. Okay, so for degeneration for family of algebraic manifolds, the cohomology group stayed, dimension stayed the same, and so on. And if you put metric structure on that, and this is still true. And here in this approximation, even if in the Gromov-Hausdorff sense, globally, you can still prove this. Okay. Actually, this is not that difficult because it's already if you prove that Gromov-Hausdorff, you have that estimate in the Gromov-Hausdorff limit. Okay. So with this, we can simply borrow something from Cheeger coding. Okay, and for example, you can say a tangent cone exists at every point and still complex, and the set of this for which no tangent cone is closed and of at codimension at least 2. So this is directly borrowed from Cheeger coding and Cheeger coding Tian, just using this approximation thing. Okay, and moreover, if this is beta I is less than 1, you can prove this is converged outside smooth topology. a smooth topology. So again, this is essentially same as the things I did before, okay, and Jeff and Toby did before. So, but there is a case, and this is certainly important, crucial in this approach, because as I said, you can make beta as big as you want, especially problem is near beta near the 1. Okay, so if this is sufficient 1, then standard argument do not apply. So okay, so these standard argument do not apply. That means in this Cheeger coding and so on. So, but by our approximation theorem, there is a sequence of smooth Keller matrix with rich curvature bounded from below by this exactly same bound and converging to the same limit space in a Gromov-Hausdorff topology. And this sequence satisfies the condition in my recent work with Bing Wang. That was the work last year, and in 2011, I guess. So on so-called almost Kähler-Einstein matrix manifolds. So M infinity is actually smooth outside the subset of a codomain at least 4. So I tell you a little difference, so what the essence of this theorem from a previous one. So what is called almost Einstein matrix is basically means I have a sequence of this matrix such that rich curvature, so it's big equal to like 1 minus some constant, say maybe I put epsilon I goes to 1, and also by topological assumptions, because this represents the first term class, you can check this rich curvature, L1 norm of rich curvature minus omega I in the L1 sense goes to 0. So in some sense, this limit, I also know omega I goes to, in the Gromov-Hausdorff sense, goes to this omega, I guess, at the beginning only d infinity. Okay. So this is a weak solution, and it's a weak limit of smooth ones. So, but this is for Einstein manifolds. And you want to say, of course, if you look at the Laplace equations, you know the limit is smooth, even though the limit is smooth, but convergence may be weak. Okay. So this is what I did with Bing Wang is a version of that for metrics. So the convergence could be weak, but limit still has sufficient regularities, has expected regularities. Okay. So this approximation theorem brought these things into this case of with Bing Wang. Okay. So then it still remains to prove if this goes to 1, this converges to omega infinity outside S. So even here, it's only a weak limit. But the things I studied is not exactly weak limit. I know this limit is smooth outside the codimension 2, a real codimension 2, a complex codimension 1 hypersurface. Okay? So I want to say this divisor, I said, does not going around and around become dense in the metric topology. Okay? So you need to prove that. So this is done by studying a limit of defining section of D. Actually, defining section is essentially 1, but this DI is just a scaling of different scaling of same section, so that the norm is 1 with respect to different metric. So then I need to prove, even in the weak sense, this sigma I converges to holomorphic section in the suitable sense. And then I want to prove a limit singularity. This S is a 0 set of that. It's actually also proof for this singular set is a hypersurface 2 in the limit. Okay, at least outside codimension 4 subset. So then one can do this. Actually, I thought about this for quite a while, and there are some technical issue here because in the Gromov-Hausdorff limit, you don't even know how to talk about convergence of complex structures. So you have to be careful. Okay, have to be careful, and without a priori, you cannot even talk about what do you mean by holomorphic section goes to holomorphic section, because there's no holomorphic section there in the limit. Okay. Even that's holomorphic section, why this holomorphic section goes to that holomorphic section? Because I cannot talk about convergent complex structure. So this is a subtle part. It's a part, and indeed you can do it. And this distinguishes the case. So here the used fact that device is fixed, or degree of device is fixed. In general, if a degree of device increases, this method fails, and you can never, in fact, you can never do same thing. Okay? And the convergence is not strong outside the singular set, outside the singular set of limit. So then once we have an extension of that, as I said, is we can use L2 estimate and use appropriate cutoff functions, and following basically the same kind of technique I studied a long time ago. So say to accept just partial C0 estimate. Okay. So this is, I stated conjecture before now, this is a theorem here. So with this partial C0 estimate, and by following arguments, I basically repeat the things here now. It's I already said that before I describe this compatibility theorem. So with this partial C0 estimate, and by following arguments, namely these few steps I stated. First, you check K-energy is proper, implies existence of Kähler-Einstein matrix. Then partial C0 estimate reduce the properties of K-energy to a properties of K-energy to a finite-dimensional case. Then use this Chini and so on and these results to say that K-energy is indeed proper. Okay, so there's some you need to do some arguments here. So in the end, you can prove if a Fallon manifold M is K-stable, then M admits the Kähler-Einstein matrix. And the converse was proved by myself in 15 years ago, okay, at least 15 years ago. So this completes the solution of four-law conjecture on the existence of Kähler-Einstein matrix. Thank you.
So how is this work related to the work of Chen and Donaldson?
And I don't know what they did. What they did?
Similar claims.
I don't think they have a compatibility how they claim. I don't think they have that compatibility how they claim.
Well, we'll see. I don't think that
I don't see any clear statement for anything in the things. This is already claimed in the things I give a talk in the Paris. And also this distributed in the private communication. I don't know any concrete claim whether you prove a cortical version of that. Okay.
Other questions? If not, let's thank our speaker.